Hello again. Tonight we're going to talk about the tension with Hubble. It's kind of a clickbaity title for YouTube just to get eyeballs on the prize. But we'll get into the actual topic of the discussion. So I'm not referring to the Hubble Space Telescope when I say Hubble, although some of the observations that we'll discuss as part of the tension is relating to observations made by the Hubble Space Telescope and not what's happening with the gyroscopes currently on Hubble. That's kind of a different topic, but as long as we're here. So for anybody that wants to know about I'll leave this slide up for a moment and just speak to it. The gyroscope count during the last refurbishment on the Hubble Space Telescope was at six good ones. We're now down to 3 good ones, and one of the 3 is starting to go a bit oddball and may fail, but it's okay. It can still do some rudimentary science with just 1 gyro. But when it gets down below 3, it's not a good sign. So NASA has tapped on the shoulder of SpaceX and said, what can you guys do with a Dragon capsule as the basis for refurbishment, another refurbishment cycle of the Hubble Space Telescope? And I went through and said, well, let me think about that for a moment. I'm not with SpaceX or NASA, but yeah, I can think. Cargo carrying capacity. The locker at the back of the capsule needs to fit whatever new solar panels, so they'd have to roll up. So it'd be packing, 2 Rolladins in there. The gyros themselves are not small. They're big boxes. So how would you fit those in the locker? Plus, if you're going to be up there for refurbishment mission, it's you may need a tank of cryogenic helium to cool the instruments on board the Hubble Space Telescope. If you remember the space shuttle actually had a decompression chamber that you had the space shuttle crew, the decompression chamber, and then the exit hatch to space. The Dragon capsule doesn't have that. You open the nose hatch, the whole capsule is now open to space. This is very much like the Gemini capsule when the US went on its first EVAs. The door opened on one side, but the whole capsule was evacuated to space. So both astronauts had to don pressure suits. And the second astronaut's door hatch had to remain closed, because if you opened it, then that means that astronaut would be exposed to the solar wind and its radiation particles and micrometeoroid impacts that the EVA astronaut had on a more protective suit to protect him from that. So if, let's say, the 4-astronaut Dragon capsule was reduced to just 2 astronauts, and you had one that went out through the nose hatch wearing an EVA suit and one that stayed inside in just a pressurized suit, that kind of thing could work. But if you remember the shuttle refurbishment missions, it always had 2 astronauts going outside to work on Hubble. One guy was standing on the Canadarm foot platform, and it was stabilizing him so he could grab tools and instruments without worrying about floating off into space. And the other astronaut was on a tether that he could grab the astronaut or grab the arm and relay tools and materials to the astronaut that was working on it. So maybe you need 3 astronauts on board the Dragon, 2 in EVA suits, but you have no Canadarm. So how that'll work, don't know. It might be that if you could modify the X-37B, it might be a more appropriate craft for servicing the Hubble Space Telescope, because it has a cargo bay, just like the space shuttle did. And there are actually NASA exploratory analysis programs that saw how to modify the X-37B to put a crew of 2 astronauts in the cargo bay in a separate compartment. Like a passenger chamber would occupy some of the cargo bay. And there's no room for astronauts up front because that's all electronics. So, yeah, lots of things to think about before somebody just goes off willy-nilly and says, yep, we'll use a SpaceX Dragon capsule to service the Hubble. But that's not what we're here to talk about. So the tension with Hubble, the what with what? The tension is referring to the differences in scientific opinions regarding observed values by which observatories and which are accurate to reality. So we've got observations made by the Hubble Space Telescope, the James Webb Space Telescope, the radio microwave background observations, and we have high energy gamma observations. And so we're looking at things like the oldest things we can find in the universe. How big is the universe? How old is the universe? And what we're finding out is the older stuff, like Hubble, comes away with a number that tells you, how old and how big the universe is. But the microwave background folks come away with a number that's about 10% older than that, 10% larger than that. And they said, just you wait. James Webb Space Telescope will solve all this stuff. It'll line up with Hubble. And the first observation that they did, I think it was late last year, it did not come into perfect alignment with the Hubble Space Telescope. It was within a reasonable tolerance, but not in alignment. It was not, to 6 sigma, as the saying goes. So they said, well, we've got future observation projects, and they'll do it again. And this time they'll get it right. They got it. They did it again, and it was off a little more. So now we've got basically 2 camps, Hubble and James Webb. And the James Webb latest are more aligning with the radio observations of microwave background. And then out of left field, they do some measurements with the gamma ray telescope observations and find that, yeah, that's kind of lining up with the cosmic microwave background and the latest James Webb. So 10% difference or tension is not that big a deal. But when you're talking about something that's, 13 billion years older, 13 billion light years across, 10% is a pretty big number. So when you're referencing Hubble tension, it's 2 things. The first is the Hubble constant, referring to the supposed constant of the expansion of the universe, and then the Hubble Space Telescope, which did some observations. So it really gets down to observational difference of opinion, how old things are, how big things are. So how do we know what's accurate, what's right, what's correct? Well, there's a model called the Standard Model of Cosmology, also referred to as the Lambda Cold Dark Model, Cold Dark Matter Model, or the Lambda CDM. It's just a postulation out there. There's no actual direct measurement of cold dark matter that would say that the Standard Model of Cosmology is proven in fact. It's just, this is what we're relying upon. And up until this tension came along, all the ducks were lined up behind Lambda CDM. And now there's the difference. There's a schism of gap between the two. So the idea is, how do we know what's right? Well, my thought is the first thing you do is you investigate these observations to see if anybody made any suppositions. So the first thing is the Hubble constant. Is the Hubble constant a constant? We currently understand this thing called the Hubble constant to be 70 kilometers or 43 miles per second per megaparsec. So every million parsecs, or every 3.62 million light years, the universe expands. The expansion rate of the universe increases by 70 kilometers per second or 43 miles per second. On every large distance, not that big change or an acceleration for that large a distance. So it's been measured. Okay, fine. But do you know that when Hubble first started investigating what we now call the Hubble constant, he came away with a different number, a number that was very much different than the number we've actually evaluated it to. He said it was 500 kilometers per second per megaparsec, because at the time they were using film, not digital measurements, so precision was a little off. And he only studied 42 galaxies. But now we have GAIA, and GAIA has studied thousands of galaxies in its survey of a good portion of the sky. The other thing wrong with Hubble's initial value was he picked the wrong horse. He was backing parallax, and as things get out further, we use different, as they call it, candles or units of measurement to measure how far things are out. And we've kept improving those things. So we've gone from parallax to candles to now we use something called sirens. And we'll down towards the bottom of the slide, we'll get into that. But whenever you make a measurement, you have to make sure that you understand the effects of your sensor, the actual mechanism by which your sensor produces data. And then when it does produce the data, you know when it's operating properly by you calibrate it to a known standard. So you expose the sensor material, you see what the values are, you plot that curve, and then when you put your instrument out in space or on an observatory and it takes a measurement, you can adjust the electronics and the software to put your sensor back in known calibration. So you know how to do it, you know what the design is, you know how to process the data, and whenever there's an early observation that has yet to be proven out, it could be that your observation is off because, oh, it wasn't properly calibrated at the time. The instrument was calibrated 2 years ago, and you're supposed to calibrate it at the beginning of every science mission. So recalibrate, try it again. Or when they went to post-process the signal data, they forgot to carry the one, as the saying goes. They didn't process the data as the design of the sensor was meant to be processing. So things can be off. So a lot of times you'll see a science team has made an observation, and then later on they'll recount it as it wasn't calibrated, wasn't used properly, you didn't obey the design rules or processing of the data. So mea culpa, they'll back out of that. But in the early days, parallax. So this is when you make a measurement from the Earth at one side of its elliptical orbit to that distant target. And then when the Earth goes around the sun and gets to the other side, you make another measurement, and you now know the angles, and you know the distance between the 2 points in the Earth's orbit, and you can use trigonometry and calculate the lengths of the apex sides to know how far away that thing is. If you've got a ground-based observatory, a ground-based observatory is good to about 1,000 light years. That's as good as parallax can do for you because you have atmospheric distortion. The Hubble Space Telescope in low Earth orbit is much better. It's good to about 16,000 light years accuracy. The GAIA, because it has the latest instrumentation and it's out at Earth-Sun L2, it's good to about 30,000 light years. But notice I didn't get into the millions or billions of light years. So using parallax is not good when you're measuring things out to the billions of light years. So the next thing they came up with is we know the color of a star helps us understand what type of star it is, and its brightness at that type says where it is in its life cycle. So we know a star of that type at that brightness, as we see it dimmer over distance, or the light shift towards red because of the expansion, we know how far away that is, and now we're to a much better accuracy, and we're out to, maybe tens to hundreds of millions of light years. So we can do that with Cepheid regular variables or type 1a supernovas. But type 1a supernovas are happening more frequently than we thought, but not all the time. So the thing you're looking at that's 13 billion light years away may not have a supernova going off in it. So how do you know how far away it is? Well, they're making some suppositions. But what we found out recently is when there's a gravitational wave collapse of two neutron stars that are orbiting each other, we know that in order to be a neutron star, you have to be of a certain size. And before they come together, we know what the spin rate is of the neutron stars, the pulsars. So we can judge if it's farther away and the wavelength is shifted, we know how much farther away it is. So if we find orbiting neutron stars, we can use the gravity wave measurement as, kind of an acoustic sound, and therefore we can use it as a siren to judge, well, if it makes this kind of waveform, this kind of transformed noise at this distance, then when we see it shifted and we think it's farther away, we can use the shift to say how much farther away it is. So now we're using gravity wave collapse of orbiting neutron stars producing sirens to get us to that next candle out farther, where we can start judging things as billions of light years away. But when you read the pronouncements of, we just found the farthest away of whatever scratch below the surface, and what are you using to judge that distance? Parallax. Sorry, not good enough. Cepheid variables. To more than a dozen billion light years, not good enough. Type 1a supernova. Okay, that's better. Or now gravitational wave collapse of interacting neutron stars, sirens, better, even still. And so we've been doing this kind of stuff, and we found out that the Hubble constant of acceleration doesn't seem to have been a constant for the entire lifespan of the universe. Maybe it was less in the earlier universe, and now it is more, because as we make digitally more accurate measurements of the acceleration, we find that the acceleration has changed over time. So the acceleration is increasing. If you know about physics, you know when you have something sitting still, it's a point, there's no velocity, there's no direction. If it's moving in a direction, then you have a velocity and a vector. That's a velocity. And then if the velocity is changing over time, going up or going down, you have an acceleration. The Hubble constant was believed to be an acceleration, as in the amount of change is the same over time. And what we're finding out is it isn't. So the Hubble constant is not a acceleration constant. It is the next step up in complex physics measurements. It's called a jerk or a jolt, if people don't like to use the word jerk. But yeah, looks like the Hubble constant isn't a constant. It's actually a change over time of an acceleration. So it's a jerk. And there's something to actually back this up. The Nobel 2011 Prize in Physics was awarded for discovering that the Hubble constant was actually not an acceleration constant, but a jerk, because they actually measured the increase in the Hubble constant over time. Now, if all you did was you had a constant acceleration, the velocity would be increasing over time. Or if you had a deceleration, the velocity would be decreasing over time. But what they're measuring is the acceleration, and the acceleration is increasing over time. So that's physics parlance, that's a jerk. So it shouldn't be the Hubble acceleration constant, it should be the Hubble jerk, and it's not a constant. So whenever you have observations made by different science teams, and they talk about the red shift, and it's towards red, which says things are moving away from us. If it's moving towards us, like a potential black dwarf star, it's moving towards us. So it's blue shifted. Small amounts in both of them. But the way that you spot redshift is by observing things that are down in the redder range. So red, infrared, mid-infrared, deep or far infrared, into microwave radio, and maybe even lower frequency radio if it were studied more. So for determining distance currently, we look at as deep an infrared as we can go, and microwave as low as the particular observing instruments will allow us. So in radio, we can go from kilohertz to megahertz to gigahertz. So that's our radio range. The Hubble Space Telescope can see visible, near infrared, through to deep or far infrared, a little bit of UV as well. The European Space Agency's GAIA can see in near infrared, but cannot at all see in mid or deep/far infrared. So when you talk about something getting redder, the moment that it gets too red to be observed by an instrument, that instrument should no longer be used for measuring distance in redshift because it can't get that far down into infrared. The James Webb Space Telescope, it can see no blues, no yellows, no greens. The first it sees is deep orange, kind of a dark reddish orange. Then it can see in red, near infrared, mid-infrared, but not deep or far infrared. So as things get more distant, as they get more red shifted, even the James Webb Space Telescope is not a good sensory platform for measuring distances that far out, although they are trying. People need to scratch below the surface and go, you just said you had a new number for, it being more than 13 point some odd billion light years out there. How did you measure that when you can't get into deep infrared? And the Euclid, same sort of thing. It can measure in visible, so it's a little better than James Webb, near infrared, but not mid or deep or far infrared. And the Transiting Exoplanet Survey Satellite, or TESS, it can see blue to visible to near infrared, but not mid or deep infrared. And then you have that new guy out there who said, hey, I'm looking at things in gamma and all high energy. I can't see anything visible. I can't see anything infrared or radio. Throw my measurements into the mix. Well, if you're looking for things that are red shifted, I don't know that I would trust observations from a gamma telescope that not only can it see red or infrared, it can't even see visible, but it's measuring it based upon energy, changes in energy levels. The next thing up is resolution or angular measurement. So if I have two things in space that are very close together, I need a certain arc seconds of separation that I can measure to be able to what is known as split those two things to know that they are two things and not one blob. So that's the angular separation, is if I've got enough resolution, if I've got enough pixels at the right density and small enough field of view over those pixels, I can now pick apart things. The Hubble Space Telescope still has the best resolution in space at 0.04 arc seconds. Now an arc second is, you've got degrees, minutes, seconds, arc seconds. So it's a very fine measurement of angular separation. GAIA has 0.07 arc seconds. It has a very wide field of view, but gigapixel imagers. So it's not as high a resolution as you think. The James Webb Space Telescope, that's kind of embarrassing, 0.1 arc seconds. A lot, you'd think from all the hype that it was much better. Well, actually, it's got a larger field of view with more pixel density across the field of view. But when you scale it down to the same degrees of field of view as Hubble, Hubble still comes out better because its field of view is narrower. So the number of pixels they spread over the degrees of field of view is such that Hubble still comes out on top. And you can see that Euclid pretty much has the same as James Webb. And then TESS, it's really coarse. But remember, TESS is only trying to detect star brightness changes as planets go in front of stars, exoplanets. So it's okay with it being 21 arc seconds because it's just measuring brightness. Now that gamma ray telescope, the Fermi GLAST telescope, it's horrible. It's 540 arc seconds. So if you're trying to measure the position of something using gamma radiation and the Fermi telescope, not a good choice for doing that. But the winner is actually ground-based radio telescopes, where you use multiple radio telescopes to synthetically create an aperture that is roughly the diameter of the Earth. So you have a multiple 1,000-mile across radio antenna, synthetically generated, it gets to 0.00012 arc seconds. And that's why, in order to image the black hole at the center of our galaxy, they used the Earth-sized Very Long Baseline Interferometry, or EVLBI, to do that. Because the black hole at the center of the galaxy is far away, and it's, from our point of view on Earth, very, 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 very small. So we need to be able to zoom in and put lots of pixels across that distance, and we can do that when we have a 8,000 mile diameter radio antenna. So we should be measuring the universe in lower and lower frequencies using larger and larger arrays of radio telescopes. But what kind of instruments are coming on the scene soon? So if you thought the Fermi Gamma telescope was going to stir the Hubble tension pot a bit, we've got some new stuff coming out. They're all in EM, but the first one is the Square Kilometer Array, and they're already prototyping this. It's going to start measuring radio from galaxies, not just galaxies, stars within galaxies, farther and farther away. It's a kilometer size, and they can actually use interferometry because the SKA has an observatory in South Africa and another one in Australia, and they can put the two of them together and get a 4,000 mile diameter SKA. So larger than a square kilometer. So 4,000 miles by 1 mile, or 4,000 kilometers by 1 kilometer. So a rectangular slot. But there's another one coming out called the Cherenkov Telescope Array that measures neutrinos in Cherenkov, that funky color of blue light. And if you looked earlier, blue, if you were looking at in space, is not the best frequency or wavelength for measuring things, but because things are shifted in red. But if you're looking for the timing, if you've got a supernova going off at the far edge of the universe and you get the neutrinos from that and you use the timing of it, now you're starting to get into things where, well, the blue is really only locally measured within the observatory. It's not blue from deep space. And so that's going to have a very high resolution and be able to measure things to very high precise levels of distance, I think. So look for future observations. But all of these proclamations of how big the universe is and how old it is, was anybody like behind the scenes fudging a bit or making postulations or foundational statements and not really telling you about them? Turns out, yeah, that's actually the case. And we'll get into some of those things. But they're trying to say we've got dark matter, and if all we did was we tweaked the dark matter a little bit and said early on in the universe's history, dark matter had a greater influence than it does today, that would make things line up better. So what was the source of this original extra intensive dark matter? We can't even say where dark matter comes from now. And you're saying back in the early universe where we have no observations, it was greater back then. What was the value of the initial rate? We don't have a measurement of that. How long did that boost in dark matter persist? And if you say it lasted for the first 2 million years, why did it suddenly stop? Why did that factor go away? So there's questions to be answered. Hopefully peer reviews where they throw in this dark matter extra fudge factor will tell us something. This one I found interesting. There's actually a Dr. Becky YouTube channel video on this. Forgive them, maybe they were wrong. It turns out there was this thing called the initial mass function that they measured the population density of different types of stars in the Milky Way. How many blue whites and oranges and reds and deep red, dwarf stars, what the population density is of each of those types. And then they just presumed that in the early universe, galaxies that exist today that have that known population density, they'd have the same population density back in the beginning of the universe. But they had no observations that would corroborate that. And in particular, now that they're only looking at things in infrared and radio, they're finding out that they have no blue or ultraviolet observations from galaxies in the early part of the universe. So the population density presumption appears to have been wrong. Now, why does that matter? You see the balance scales in the lower right? Well, turns out if you have a lot more red dwarfs or orange dwarfs than the number of blue or UV stars that you presumed were there that don't seem to actually be there, then the reds can outweigh the blues, and the balance of forces in your early on galaxy aren't quite what you just presumed them to be. The presumption that the population of star types in the Milky Way has always been that way for all galaxies throughout time and throughout the universe. That's apparently not the case, but given that they were standing on that porch step for a long time, I look at it as the universe is probably older than they previously thought, because the initial mass function seems to have been off. And it was off because they just presumed that there'd be that many blue, but they have no instruments capable of measuring blue that far back. It's science, folks. It's not dogma. So points along a curve. Whenever you have several observational points, if there's a progression or a degeneration or an expansion or whatever, you want more and more points along the curve, and you want more and more points along towards the endpoints of the curve. And as you get more and more points, you can see what the actual curve is, as opposed to the curve may be wiggly and they change over time. So we're finding out things like, well, that acceleration that we thought was the Hubble constant is actually a jerk, not a constant acceleration. Maybe the jerk was even more different early on in the universe. We have no data to back that up. We just are making an assumption. But the acceleration value maybe diminishes with time due to Higgs field interactions, because we're now realizing that there's this thing called the Higgs field that is everywhere, but we don't quite understand what it is and how it affects things. So it could be that things like the speed of light is limited to c, because the Higgs field kind of keeps a constraint on things, so you can't go any faster. Even if you apply all the energy, it wouldn't let you. But I look at this and say, I always like analogies. I always like to say, how would this apply in a model that I could show people? How about a balloon? You take a rubber balloon, and when you go to blow it up, the initial amount of air you have to put into it is greater than the amount of air you have to put into it to expand it more than 50%. So the first like 1/4 expansion takes more energy because you're fighting the resistance of the expansion of the balloon. You're fighting literally the rubber molecules wanting to hold things together, and then the air pressure you put in it finally gets to a threshold, and now it expands more easily. Okay, that's my analogy. What if you had a balloon inside of a partially filled balloon? How much more would it take? Well, it should take more, but the point at which the inner balloon that you're blowing up would expand and come into contact with and start expanding the outer balloon means you have to not only expand the rubber molecules, you have to fight the existing air pressure in the outer balloon. And until you conquer that, you can't see the rate of expansion suddenly get greater. So I look at it and say, if you want to think about the universe early on having slightly different constants than it does now, and we're seeing the constants changing over time, then maybe the early universe had something that was holding it back. You know, it came into existence and started to expand, and the expansion supposedly just went everywhere instantaneously. We don't have, I mean, that's just a supposition, but maybe it was more a matter of, you know, started to expand and then it expanded more slowly. It was still under a lot of force, but expanded more slowly for a time, and now it's expanding faster. Balloon or balloon within a partially filled balloon. As the saying goes, you heard it here first, but it may not last any longer than spoiled milk. So we've made these measurements, and they're the source of tension with the Hubble constant. Actually, no, they're not. There are other observations that we've made. Things don't seem to be working out right. The math is not coming up right. Star cluster M92 in the Milky Way galaxy, at the edge of the galaxy, they started looking at some of the stars in that cluster, and they measured what would be their color and redshift and found that how can those stars be 10 billion years older than the universe, than the galaxy? That just doesn't make sense. How can they be older than the galaxy? Well, if they're part of the galaxy, that doesn't seem to make sense. But what if that cluster of stars was actually ejected with high velocity during the early existence of the universe and just happened to come in our neighborhood, and the Milky Way galaxy's gravitational field snared that cluster of stars, and it's now a dweller on the outside of our galaxy. So that would allow stars in M92 to be older than the galaxy itself. So there's a way you can think about these things, but that would only allow the stars in the cluster to be older than the Milky Way. It would not allow them to be older than the universe. In my book, let's do some more peer review on that. But then again, we find things beyond our galaxy. There is actually something known as, in the Abell catalog, item 2744, also known as Pandora's cluster. It's about 4 billion light years away from Earth. It's not a cluster of stars, but it's a cluster of galaxies. Each of the galaxies with potentially billions of stars. So they've observed this using the near-infrared camera aboard JWST, and they've observed it both directly on the outer edges of the galaxy cluster, and inside the galaxy cluster, there's enough gravity that it actually acts like a lens, like an Einstein ring, and they can see even more distant galaxies using the ring, and those are older than the universe. So is it the fact that they've been magnified that somehow changes their redshift so they look older than the universe when they're only as old as the universe? So we looked at it in other frequencies, and we looked at it in X-rays. That's the middle one is Chandra. And then we looked at it in radio using the improved giant meter radio telescope. It's just a single telescope in the 550 to 850 megahertz range. And obviously both the Chandra and the UGMRT are false colored because you can't see radio waves and you can't see X-rays. But these are all of the same celestial target, and you can see that the radio actually shows a fog in the center of what would be the gravitational magnification area. And that may be affecting magnetic fields, which would maybe affect bending of the light, which might make it look older than it really is. So Pandora's cluster, put a push pin in that, let's see where they come up with it. But that's another source of tension. So it's not just the direct measurement stuff, it's all the indirect measurement stuff that now says, is it older than we think it is? So here's another one. Currently, the universe is believed to be 13.8 billion years old, but we're now seeing observations from JWST at the most distant galaxies that we're measuring in mid-infrared, not radio, that are coming back saying, oh, maybe the universe is more like about twice that. Remember me saying that look back to the history of measurements, and sometimes the initial measurements can be quite off. And when you learn a little more, your measurements might be a lot better. And nobody remembers the good old days when we measured the universe as being only 500 million years old. That was in the last century. So in 1929, before the Hubble constant came into existence, there was a physicist called Fritz Zwicky, and he proposed that in addition to redshift, maybe high energy photons at very, very far distances back into the early part of the universe, something called tired photons, or a photon going all that distance through all that stuff of deep space might actually lose energy. In other words, the photon starts out from someplace like a star, and then it starts traversing the universe, and it runs into all sorts of dust and debris and clouds, and the photon gets absorbed, but because it's so high energy, it gets re-emitted, but not at 100% of its original energy level. It might be that some of that energy gets re-emitted as infrared heat way off in the distance. So the very, very high energy, gamma photon starts out as high energy gamma, and then over the multiple billions of light years actually shifts from gamma to less gamma to high X-ray to X-ray, and it comes down a degeneration curve based upon all the stuff that it had to go through. But we have no data from back then. All we have is the data we can see now. So it may be that some of the things that we're seeing that are redder when they first started out weren't redder, they were bluer or higher energy. And we can keep the redshift because that's kind of proven science. But we have this tension, this gap between observations we're now seeing with better instruments and what we thought of as being the stake in the ground of 13.8 billion years old. And if we were to also roll in the Fritz Zwicky tired photon concept, we may actually find a coverage for getting it out to 20 plus billion years. But that's for the future to decide. So keep your push pins in place. Whatever somebody says now is the matter of fact. It's only the matter of fact until things get better at measuring things, or somebody blows away a postulation that with further observation proved to not be what you think it is. So sometimes short-lived things are okay for the time being, but ultimately never assume that when you put a stake in the ground that there can't be another stake that's better coming just down the road, not too far along. But the true darkness, not dark energy, not dark matter, but not publicly disclosing your earlier finding had an underlying presumption, like UV or blue stars that weren't actually there in the early universe. But since you didn't have any data, you just presume everything's going to look hunky-dory, just like the Milky Way does today. And it seems like that's not the case. So in conclusion, science can get it wrong, and that's okay. But when you dig below the surface and you find out historical facts, you should appreciate that as that's what we knew back then, but now we know better. And maybe tired photons are something we ought to look at again. So as newer observations come in and get confirmed, there are newer opinions, and maybe things are older or the universe is larger than we thought. But sometimes, the harder you drive the stake in the ground, the more difficult it is to pull it up and move it a little farther down. But we've done these kind of things in the past. The sun once revolved around the earth, and we realized that's dumb. And then we thought, well, the earth is the center of the universe, and that's dumb. And there are galaxies, not nebulas. But even in the last decade, it's the Hubble jerk, not the Hubble acceleration constant. It's just, unless there was a lot of media published stuff about that, people wouldn't know about that, wouldn't know that the Hubble constant, it's not a constant. It's actually a jerk. We need to keep an open mind. Don't come up with postulations that you don't want proven out and you have a problem with them being proven wrong. Do identify when there's discrepancies, and if there's no data yet, no observations yet to say one way or the other, or a collection of observations that are peer-reviewed, then it's okay to postulate and go, you got a gap here. There's Hubble tension. Maybe there's a way you can adjust for that, and give it a try. Maybe it is tired photons, or maybe it's the inflating a balloon within a partially inflated balloon. Who knows? And of course, lots of links on all this stuff for the truly deep divers. Oh, and that thing in the center of Pandora's galaxy cluster, that's referred to as a radio halo. And then if you're into Cherenkov radiation, you can see the Cherenkov Telescope Array Observatory. I'm on their mailing list. Not that I'm involved in their project, but it's a push pin. I like to keep an eye on it. Okay, so Diane just started with hey, there seems to be multiple observations saying the universe is different sizes and distances. What's all that about? So that's when I started studying it and said, yep, that's a thing. Hey, who knew the Hubble constant was a jerk and not an acceleration? And then you start scratching below the surface and you find, hey, there's postulations that they made that they had no observational data to back it up. They just said, well, things are that way now. They must have always been that way. Comments? Questions?
I have a comment.
Yes.
It's not a question, it's a comment. And I know, because you have said several times during this presentation, that we should forgive scientists for being wrong because they didn't have tools then. They didn't know that this wasn't a fact. But what I bring up as a statement is and my thought, opinion. I know that other people have other opinions about this, but I don't get upset with people that challenge and say, I don't believe science, because it has got things wrong. And when they say, well, I'm not going to do this or that because I don't believe that they have it right. Mm-hmm. They may be correct that they don't have it right, even though we think we have it right now, because we've done so many tests and we've verified it so many times that it came back that, and sometimes it's good that people keep questioning things. That's my comment.
Well, I understand the basis of it, and I agree to part of it, which is it's okay to question statements, public ones made by scientists. It's okay to question them, but don't deny them. Don't outright go, I don't believe you, without, saying, well, the reason why I don't believe you is this other group of scientists over here said the number is 7, not 12. I can say, I see the tension, I see the disagreement. Therefore, it's not that I don't believe you. It's I'm going to scratch below the surface of your pronouncement and go, oh, you made a presumption.
Yes, and they made presumptions, and I'm sorry, Monroe. Are you done? Can I make another comment on your comment?
Go ahead.
Okay, my comment on your comment is that you're saying, or what I hear you saying, or what I hear other people say too, is that, oh, you should have another scientist back you up. But even tonight, when you were talking, you said about scientists making assumptions. And that's how they got things wrong a lot of times, is because they made assumptions. But sometimes assumptions are not wrong. They are correct.
Yes.
And sometimes people are not scientists, but they have, and there's been people that have discovered things that were not scientists in and of themselves before they discovered something and brought it to attention and went through the whole mumble jumble. They weren't scientists in the beginning, but they just had a hunch. They just knew that this was not the way it should be. And just because they didn't have other people to agree with them and back them up, I don't think that's the only way you can disagree with somebody and not say, oh, well, you don't have anybody else agree with you. You should not say that. That's not my opinion. That is not what I find fault with that. But I usually, because I believe in scientists, and that's why I come here and I hear the new things and how it changes. And I'm more inclined to go along with those things that come out and are published by scientists and, medicine. I follow those things and look at what's going on with that.
I don't have to disagree with them. Facts disagree with them. Actual facts said, this is the way it is. Now, when it comes to things at the bleeding edge of science, like how big is the universe? How old is the universe? What did the universe look like in its early days? Science is still struggling with that one. And they've got some postulations and they're making observations. So you can kind of throw a monkey wrench with your own observations into that mechanism. But at this point, if somebody came along and said, the universe is steady state, it's not Big Bang. Well, you can, have doubt as to what the bang was, when the bang was, how big the bang was. But the fact that the universe has changed over time and there is expansion going on, that's kind of a done deal. So the whole steady state universe, if somebody walks up and says, I disagree, I think the universe is steady state, you can have an opinion, but your opinion is probably not going to carry a lot of weight with the majority of people who understand things better and know better. As for certain scientific policies of governments, I think a lot of it is governments like to appear as though they're your parents. They have knowledge, they have awareness. They were elected as your parents to say, this is what we're going to do. It may not be right, and just letting the dice roll doesn't seem to be a good approach. So this is what we're going to do. And whether that saved lives or not versus how much it distorted kids' minds because they had to stay at home too long, or parents' bank accounts because they couldn't afford to stay at home with the kids. That's a societal thing. That's not science. Of course, my humble opinion.
Well, Joanne used the phrase "got it right," got it right.
Mm-hmm.
There's degrees of got it right, and we go with what seems to be the most probable truth.
Yep.
Whether or not a battery is going to give me 1.5 volts or 1.6 volts or 0.3 volts. You go with what you think you got.
Well, there are standards.
Yeah.
Government and industry put into place standards that says if you go buy yourself a AAA sized battery, it's going to produce a certain voltage and give you a certain number of watt hours of electron flow output. If you go buy a 26650 sized lithium battery, it's going to give you a different voltage for a different watt hour. And there are standards for that stuff. Yeah. And it turns out that those standards are pretty much based upon the chemistry, the physics of the battery components. So if somebody comes out,
it's not a matter of opinion. It's a matter of
it's a matter of scientific proven fact, right. And it's not one person's opinion. It's so many people's opinion that you can actually put a standard out that says if you're using this chemistry, this is what you're going to get in this size battery for this period of time. So,
but which is also, the other thing is that it's also a matter of being able to make predictions and testing them and finding out the predictions are correct. What science does is it makes predictions and it says it's correct or not. So when Monroe, you're saying, yeah, we figure this out, and this particular chemistry and this particular size of cathode and stuff is going to give this. That's just another example. It's an example of science making predictions and being able to predict. And a lot of what you get of people who have, certainly some people have hunches and they turn out to be right, but lots of them aren't.
So, at what point do you have faith in something? And at what point do you say, well, hasn't been proven by everybody on the planet yet, so it's not science. Well, how about it's just been proven by the people with the education, experience, training, and even the naysayers within their own groups that have come around, so to speak. Because remember, in cosmology, the steady state universe was actually joking when they referred to its opposition as the Big Bang. And the moniker stayed with it even after it was identified as, well, that seems to be the way that works. So, yes, in sociological terms, human existence as a population is complex, and opinion has its place, and opinion absent information or absent observation should not be as valued as opinion based upon observation, peer proven and substance. Anyway, so we're closing on the bewitching hour. We made it.
That's it. Yeah, we made it.
Monroe, thank you very much for doing that presentation. That was my suggestion, and I appreciate
I
it.
reshaped it. I reshaped it quite a
interesting.
bit, but it was your impulse that led me into the initial rabbit hole to go in there and make my way to the bottom. And Adam has
So-
one on.
Yes,
Wait,
it was a
did
very
you-
good topic. Thank you.
Thank you.
Okay,
Stay
Did you
well.
say that?
okay. I'll stop waxing now.
I guess you're still recording. You could go off of that.
Yeah, okay. So I will stop recording at this point.